All right, so again, welcome to the Math 136 live lectures. This is for review for your final exam. This is one of 3 lectures that we had for review. You probably are aware of the review because your teacher either posted it in your class or you received a message that came to your email because we had that sent out to the students as they are enrolled for Math 136. My name is Debbie Yaus, and I'm doing the review tonight. Saturday session was held by Paul Camber, and tomorrow there's another session Tuesday at 1:30 that is held by Brenneman. And so you can attend that one if you wish as well. So we are going to get started, and I'm going to let you know how things are going for this session. So everyone should have somewhere in their class, and I'm going to see if I can open it, had some type of announcement posted from your teacher somewhere, or maybe added a link on the homepage to the live lecture schedule. And in that schedule is a link, and also in the email that went out was a link to some practice problems that we prepared in preparation for the final. So if I click to that section in this schedule, a little slow, it's catching up. We sent those questions here. So if you've had a chance to look at those in advance, that's what I'm using tonight. I will let you know that this recording from Saturday has been posted today. So feel free to go back to do that. Paul was able to go over questions 1 through 7 as part of that review. And so my plan for this evening is to ask you, the students who are here live, what questions do you have? And I will start with the questions you have, even if it's out of order. And even if it's something from problems 1 through 7. And if nobody has questions, then my plan of attack is basically to pick up with problem 8 and just continue where Paul left off, since we already have a recording here for problems 1 through 7. But again, you're here live, so I'd rather take your guys' questions if you have them. So if you have specific problem numbers that are from the review that you want to ask about, then you can go ahead and put that in the chat, and I will take them in the order that people are asking them. If this is the first time you're looking at this and you don't have any questions, like I said, that's totally fine. I will just probably pick up with problem 8 and keep going unless somebody interjects and says, you know what, can you actually skip to such and such problem number to do that? The other thing that was posted for students was a study guide. And I have that here on the screen just to show briefly here. This really breaks it down section by section, topic by topic. And then we gave some tips and reminders of like, what are important formulas to know in that section? What are some things to look out for or remember that students forget that might be helpful, and things like that. So I suggest trying to use this like a checkoff list to say, okay, as you're studying, do I know this formula? Do I know this process? Do I know how to use that and apply that in a problem? And if you don't, then maybe that's something you highlight and circle, and you know you have to go back and study that. So again, it covers all the sections that are included on your final exam, just to give you an overview of things. So you kind of had it in one place and didn't have to flip through your notes or through your modules in your course for things like that. So I recommend that you utilize this for that. The other thing I want to make sure everybody is aware of is, as it's stated in your course, you do have a formula sheet that is provided in the course that you should be able to use at your proctored appointment. You probably remember from the midterm, there wasn't a whole lot on the formula sheet that applied to the midterm, but there is a lot more on the formula sheet that does apply to the final. And so probably starting at simple interest and downward is all related to content that is in sections that are related to your final exam. Now, if something's not on this sheet, it doesn't necessarily mean you don't need to know it. It just means it's not something we're providing to you. And so you do need to know it on your own without just referring to it on the formula sheet. So make sure you're aware of what's on it and what's not on it as you prepare and study to take your exam. So with that said, there are 20 questions on this set of review problems. There are 20 questions that are on your final exam. We tried to pick problems that were very similar in terms of topics for what would prepare you best for it, okay? So I was just gonna say, I don't see anything in the chat, and then someone put something in the chat, so this is perfect. So again, feel free to add to the chat. I will go over as much as I can until 7 o'clock, and we'll see where we go from there. So as I go over these, it looks like I'm starting with 19 and 20. Feel free to put more in there, or if you have questions as I'm going through the problem and you don't understand a step that I took or something, please do ask. We want these sessions to be for you guys, the student, and be able to ask questions and make sure you understand things. 19 and 20 are, I think, similar. Yeah, they are similar. One of them, 19, is related to exponential growth. And then 20 is related to exponential decay. And so those are very much related topics. And a lot of how you solve one is very similar to how you solve the other, just to try and make that connection there for you. So I'll start with 19. And these are going to involve exponential equations and then also probably logarithms in terms of how we solve. So I'm going to start with 19. So it says the size P of a certain insect population at time T that's given in days obeys the function P of T equals 900 times E to the 0.02 T. So when it says it obeys that function, it basically is modeled by that function or follows that. So the first part, determine the number of insects at T equals 0 days with that. So at T equals 0 days, that is giving us the T value. And so our function has a variable of T that is the input or the domain values into the function. So what this is telling us is if T equals 0 days, then we need to evaluate and find P of 0. And I need to just turn something around here on my computer so I can write better. Okay, so that means that this is 900 times E to the 0.02 times 0. And so that's taking 900 times E, the 0.02 times 0 is 0. And E to the 0 is 1. So this is just 900 times 1, or 900. Now, you could do it that way, and you would get that there are 900 insects. The other way you could have done this without actually doing any calculation that actually would be more efficient and faster, which is sometimes important when you're at the test because you might be crunched for time, is this value that's in front of the, let me write that clearer, that is in front of the exponential part E raised to the power is always your initial value. And initial value means at that starting time 0. So I could have just looked at this and said, oh, that's my initial value, because my formula is basically P of T equals P sub 0, or P naught, we call it, times E to the KT. And that P sub 0 is that initial value. So you could have done it that way as well. Then on part B, it says, what is the growth rate? And so it's important that this says rate. Notice here, it also has a percent sign. So it's looking for a percentage as an answer, not a decimal. So back up to the standard form here, the K value in that format is your growth rate if K is larger than 0. In other words, it's positive. And so in our equation, we have 0.02. And so I need 0.02, but I need it as a percentage. So we can multiply by 100, or we can move the decimal point to the other side, or move the decimal point 2 places to the right, and it accomplishes the same thing. So either multiplying by 100 or moving the decimal point. And so I know that my answer is 2, and I don't have to write the percent sign because they already put the percent sign there. And because they put the percent sign there, I also know I don't need to put in 0.02, that I need to put in the 2 instead. And because they use the word rate is another clue that you know that you're using the percentage for that. So those are kind of key things to look for. Part C, what is the population after 10 days? So after 10 days, that's very similar to the first question when I first substituted in 0 without just jumping right to the fact that the value in front of e raised to the power was the initial value. This is now saying, we'll just plug 10 into your function. So we're going to find p of 10, which is 900 times e to the 0.02 times 10. Now at this point, you're going to reach for your calculator. And I need to reach for my calculator. So on your calculator, depending on the type and brand that you have, Scientific, Graphing, Casio, TI, even the different TIs and Casios, you're doing something different depending on what you have, but you're all looking for an E button. So it's usually probably something that looks like e to the x on your calculator that you're looking for a button for. Now, you can make this easier for yourself by pre-multiplying the 0.02 times 10 if you wish. If you don't, then I would just suggest that you have an extra set of parentheses if you enter it exactly how I have it written on the screen. That way it's including the times 10 as part of the exponent and not just cutting your exponent off at 0.02 and then thinking that it's taking the whole quantity you're entering times 10. So you're kind of forcing it to follow a specific order of operations. If you wanted to, though, you could just, like I said, pre-multiply that so that the 0.02 times 10 is just 0.2, and then you don't have to worry so much about that. But most calculators will automatically open a set of parentheses when you go to put in the exponent, and then you'll have to close the parenthesis, even if you just put in the one number. So that's what you're putting in your calculator. And if you put that in your calculator, notice that it also says, do not round until the final answer, and then round to the nearest whole number. Do you want to pay extra special attention to the extra instructions that are down underneath the problems in MyLab so that you don't lose points simply because you didn't put it in the correct form? Now, your instructors are going to go back and grade your tests for partial credit and look at your work that you submit on paper. So I highly recommend that you write out the steps and the values like what I'm doing here before you put it into your calculator, so that they're looking at your paper and they can see, like, you know, you just had a rounding mistake, you know, from calculator to MyLab or something like that. It's to the discretion of each teacher how much partial credit they give, but most will give some type of credit for that in some way. So this turns out to be, oops, I want my highlighter. This turns out to be approximately 1,099 as a whole number. And so that's what you would be entering, okay? And again, if anybody has any questions along any of these steps, please let me know. Then part D says, when will the population reach 1,350 insects? So when it says when, that means we're looking for T. They're not giving us T like in the previous example. We're looking for T. And the fact that the population is reaching 1,350 insects means find T when P of T equals 1,350. And so that means that the whole equation is equal to 1,350. And so we are going to solve 1,350 equal to 900 times e to the 0.02t, okay? So we need to get t by itself. And so e raised to the 0.02t is currently multiplied by 900. So the first thing you can do is you can divide each side by 900 to get rid of that on the right-hand side. After you do that, I'm going to go ahead and simplify that by dividing each of those by a power of 10 there, so that I can simplify this to 135 over 90. equaling e to the 0.02 t. Because if you try and divide 135 by 90, in this case, and it's unique to this case, we actually get a terminating decimal. If you divide that, you do get 1.5. So you could use 1.5, but word of caution, if you divide something like that and you do not get a terminating decimal, it doesn't stop, it like goes to the end of your calculator screen. That doesn't mean it stops at the end of your screen. It means that that's just how big your display is. And so if you try and round something right then, you're gonna get an inaccurate answer. So once again, I'm gonna go back to these directions that are underneath the blank. They say don't round until the final answer. So if you need to leave something as a fraction, because it doesn't divide equally, I'm going to show you what that would look like. So I'm not going to write that as 1.5, just to show you what you would continue to do if you had to leave it as a fraction, because on some of them you will have to. Okay. So at this point, you have two options. And it really depends on how you see the problem. So you could, at this point, take what is basically the inverse of a base e, okay, an exponential function, which is applying a logarithm, okay, specifically a natural logarithm. So one thing I can do is I can come in here and apply the natural logarithm, or ln, to each side. And remember, that isn't L, it's ln, not in. And what that does is, because of properties we have with inverse functions, the natural log of e raised to the 0.02t on the right-hand side has the natural log and the e basically negate each other. And that drops down your power to just simply be 0.02t, and the natural log of the e part goes away. And then on the other side, you've got the natural log of this quantity that I left as a fraction, 135 over 90. Now you go back to your normal arithmetic rules. If you want to get t by itself and it's multiplied by 0.02, then you just divide by 0.02 on each side. I'm going to divide by 0.02, divide by 0.02, and that's going to tell me that the exact answer for t is natural log of 135 over 90 divided by 0.02. And that's what I'm putting in my calculator. Now, when I put that in my calculator, again, it's really important that you have these parentheses around what goes into the natural log, okay? And then you're dividing by the 0.02. If you forget to close off this second parenthesis, it's going to want to put the division by 0.02 up in line with what's going into the natural log, and you're going to get a completely wrong value. Okay, so the parentheses are really, really important for that. And then I'm going to check how it says to round. So it says round it to the nearest tenth. And so if you put that in your calculator correctly, round to the nearest tenth, I believe you should get on this one 20.3. So this is 20.3 days that you would get for that. Now, that's one way to solve this. Other way to solve this is, and again, this is totally on your perspective and what you see when you look at this. So I'm going to say, or the other way I could have done this is, remember, I had 135 over 90 equals e to the 0.0t at this stage. And what I did is I applied the natural log to each side. And the reason I could do that for this was, if m equals n, then log base a of m equals log base a of n. In other words, you have two quantities that are equal on each side. You can apply a logarithm with the same base to each side. I chose to apply a natural log with base e to each side. And that was because I had a base e already in the problem. But over here, alternatively, what I could do is use the definition of a log to switch forms. So our definition of a log is y equals, and I might be using slightly different letters than maybe what was in your text, but if y equals log base a of x, if and only if x equals log base a sorry. I was trying not to go off the edge of the paper and then I started writing it wrong. If x equals a to the y. There we go. So you know that basically you have log form on the left, and then equivalent to that, you have, I'm abbreviating here, exponential form. And so what we've got basically is this exponential form. And in place of x is 135 over 90. In place of my base a is e. And in place of y is 0.02 t. Okay, so again, this is y. My base e is like a. And the 135 over 90 is the x. So then if I switch forms, the x goes as the input to the logarithm. The logarithm has the same base. And then what it's all equal to is the y. So now if I rearrange all that, then this all turns into the natural log, because that's base e. So it'd be log base e, but we don't really write it that way. We write natural log of 135 over 90 equals 0.02 t. So highlighting in the same spots, here's where the 0.02 t went to for the y. Here is where my base and logarithm went, because natural log is base e. And then here is where my x went. And notice that's the same thing that I got here before I divided by 0.02. Same step, just got to it a different route. So some people like to think of it as I'm switching forms using the definition. Other people like to look at it as I'm taking the natural log of each side. You do what makes more sense to you. I've had classes where I have like a portion of my class who like it one way and another portion of my class who like it the other way. All right, so then E, when will the insect population double? So there's that question again, when? So when you see when, that means you need to find T. Well, find it when what? Well, in the previous one, it was when we reached a certain quantity of insects that they gave us. This one says when the population doubles. So it's not a definitive amount. However, remember part A told us at time 0, which was our initial value, we started with 900 insects. So I know from that double is twice 900, which is 1800. So I need to find T when P of T equals 1800. And so for that reason, part E is almost identical to part D. The only difference is where there's a 1350, I'm putting 1800, okay? So I would solve 1800 equals 900 times E, 0.02 T. I would divide by 900 on each side. And I'm going to go a little fast on this step because it is exactly mirroring what I already explained in pretty much good detail, I think, in the other one. But please stop me if you do have a question with where I'm going here. So that's 2 equals e to the 0.02 t. I like to apply natural log to each side. That's the way I prefer to look at it. And so then that gives me natural log of 2 equals 0.02 t. And now I can divide by 0.02 on each side. And that gives me an exact answer of natural log of 2 divided by 0.02 equaling t. And that's what I would put into my calculator. So I put that into my calculator. I check my rounding. I don't round until the end. And I go to the nearest tenth. And so then this is approximately 34.7. And so that is part E. Okay. Oh, we can skip 20 and go to the other two since that took so much time. Yeah, so if anybody has any specific questions with number 20 that you want me to see and work out, let me know. But yeah, I'm happy to skip 20 because it is very parallel to what just happened in 19. The only difference would be is like, for example, half-life, then obviously you're not using double, you're using half of what the initial value is, but same concept, just opposite direction of, you know, a double amount versus a half amount. So getting a smaller amount. And then the other thing to remember is A of t equals a sub 0, that is still the initial amount, times e to the kt if k is less than 0. That's how you know it's a decay. And so you can see right there, there's a negative sign because k is less than 0. So that's how you know it's a decay, even if it didn't say the word decay in the problem. So, so yeah, if anybody has anything, but since the person who asked for the actual 19 and 20 is saying we can go ahead and skip 20, I will go ahead and do that, but I'm happy to circle back around to that if anybody wants me to, okay? All right, fantastic. So I see 12 and 13. 12 or 13, okay. So let's take a look at that. Okay, so let me see how closely related they are to see if similar to 19 and 20 that I can kind of explain them together, or if they really truly are different, because I'm happy to do both of them depending on time here, if they truly are different. So 12, all right, so log of x plus 1 and then plus a 3, and it's going to ask you some things about domain, getting the graph, range, asymptotes, inverse, domain and range of inverse, okay? And then 13. So 13 isn't actually with graphing. So they are completely different. So I can do both of them if you want me to, because they are different with that, unless you meant a different one with graphing. But I'll go ahead and start with number 12. And so with that, when the log is just written and there's no subscript underneath, then that means that's the common log. And so that is common log with base 10. So it's just understood that it's base 10. So similar to how we write ln for natural log, that's understood that that's base e, okay? So that's base 10. So the common log with base 10 of the input x plus 1 and then plus 3. So the first part on A says find the domain of f. So domain always refers to what's going into your function, okay? And so I looked at 13 incorrectly. I understand that one. Okay, if anybody else does want 13, just let me know when I get done with number 12, and I am happy to do number 13 as well. So domain is always referring to what's going into your logarithm. And notice again, special instructions, type your answer as using interval notation. So that's using parentheses or brackets, starting at one value, going to another value. So again, you want to make sure you're entering things in correctly as well as understanding the actual value of the answer. So for logarithms, remember that for logs, the input to the log must be greater than 0. So whatever goes into the input, well, the input is this expression x plus 1. That's the input for this particular logarithm. So that means for this problem, we need x plus 1 to be greater than 0. So we needed to solve for what values of x make that happen. So this is a linear inequality. And so that's something you did, I don't remember in what section, I want to say like maybe 1.5, 1.6, but it was all the way at the beginning of the semester or beginning of the term as part of week 1 or week 2. And so you solve it just like equations, just being careful that if you have to divide by a negative value that you flip and your sign around, or if you divide by a negative value or multiply by a negative value. But here we would just be subtracting 1 from each side. And so we don't have to flip anything around. And I get x is greater than -1. So the only values that make the entire input expression larger than 0 are when I use an actual x value that, remember, is going to get added to 1 as well, that is larger than -1. But I need to write that as an interval. And so that turns into starting at -1 and going to infinity. So because I have no equality there, I've got just greater than, I have to have a parenthesis. If it was greater than or equal to, which for the domain of this function is never going to be equal to because it's always greater than 0 that you need that whole input to be, I could use a bracket. But I'm going to use a parenthesis. So it'd be parenthesis -1 to infinity. And remember, infinity always has a parenthesis around it because you can never include it. It doesn't end for that. So that's our domain. So what that also means in relation to what we're going to do in part B with the graph is that we shouldn't see anything on the graph outside of those values left to right. So domain refers to X. That's left to right on your graph. And so, you know, I know a lot of the problems in my lab say to choose your graph and you're not like drawing it by hand. But here's the other thing. This is also related to transformations. So I'm going to take that and I'm going to say, how is this related transformations? So I'm just going to rewrite it so I have space over here. Okay, so if I was comparing this to what I call a parent function or a base function, it would just simply be y equals common log of 10 of x. And there'd be no other numbers with it. But there are other numbers with it. The x has a +1. And outside of the input to the logarithm, there's a +3. So I have to think about what does that mean in transformations, which again is review content from, I believe, stuff that was included on your midterm. So if you have a +1 related to the x, that's horizontal because it's affecting the x. And so what this means is you have a horizontal shift, and it's a shift because it's related to addition or subtraction. So something affecting x with plus or minus addition or subtraction is a horizontal shift. The question becomes, which way? So this is the one where I always tell my students, you go against what your gut wants you to do. So your brain sees the plus sign and your brain's going to want to go to your right, but that's not right. The horizontal ones always go against what your brain wants you to do. You're going to do the opposite. So it's a horizontal shift left 1 unit, okay? Then you look at the +3. The +3 is on the outside of the function. And the outside I'm referring to is basically not the input to the log. So the input to the log was x +1. And then that's your function. And then you add 3 more onto it. Well, if you add 3 more onto your function, remember your function is equal to y. Y is vertical, okay? So that is telling me this is vertical. And then in terms of, is it a shift? Is it a stretch? Is it a compression? It's, again, a shift because I have something added or subtracted, in this case, added. If something was multiplied, then I'm talking about compressions and stretches, okay? So if you look at the operation, it's plus. Now, vertical movement follows what you see. So it doesn't go against what your gut says. So your eyes see the plus and you want to go up because that's where plus normally is, or positive values. So this is vertical shift up 3 units. Well, that means the entire graph moves that way. So what that means is back over here, I can't have anything that is to the left of -1 because of my domain. My domain was -1 to infinity. And the fact that there was a horizontal shift left 1 unit makes sense because the normal domain of the parent function is values of x greater than 0, or basically 0 to infinity. So if the whole graph was shifted to the left 1, that's why the domain also shifted to the left 1 starting at -1, okay? And then the whole graph lifts up. So what you might remember for a log function, just its very rough sketch, is that it passes through an x-intercept of 1, 0. And then it has what we call a vertical asymptote at x equals 0. So if I take all of that and I shift left 1 and up 3, then that point 1, 0 is also going to move left 1 and up 3. So that point 1, 0 becomes left 1, so it's going to be 0 for the x value, and up 3, so the 0 is going to go up 3 and become 3. And so that's its new point. The asymptote is also going to be affected. Well, moving the graph up of a vertical line doesn't affect it, but moving the graph left does. So that's going to have to become x equals -1 for the asymptote. So those are kind of the things I'm looking for when I look at those graphs with multiple choice. So for that reason, I know I can't use graph B because it's below the x-axis. That didn't move up, it moved down. Same thing with D. That graph was moved down below the x-axis. So that doesn't match with the move up 3. And so then I look at A and C. And if I look at A and C, and I'm just going to zoom in on this. If I look at C, notice that this is to the right of the y-axis, as opposed to A, which is to the left of the y-axis, which makes sense because we moved to the left 1. And so our answer is A. Okay. And I can see it was moved up 3 along with that. So that goes along with the other part that I was saying as well. Okay. All right. So then it says, from the graph, determine the range and any asymptotes of S. Well, I actually already talked about the asymptote, so that's convenient. But if I talk about the range, so looking at the graph in A, range is from bottom to top. And so I can see that that graph is going down indefinitely, and then it's curving over to the right and gradually rising. Well, that's going to keep gradually rising all the way across its domain, which goes to infinity. So if it's going to keep gradually rising vertically, then the range is going to also go to infinity. So the range here, which again says to type in interval notation, is going to have to go from -infinity to infinity, from, again, bottom to top of the graph. And then it says determine the vertical asymptote. So I already talked about that. That's why it's important to know what kind of transformations have happened. So the vertical asymptote normally would be x equals 0. Well, now it's shifted to be x equals -1. And so you have to be very careful. Notice answer A already has the x equals there. So you just need to put in the -1. You don't need to rewrite x equals. So it is an equation. It's for a vertical line. And vertical lines are all equations. So if I was writing it on my paper, I would write it as an equation. I wouldn't just write the number -1. But in my lab, because the x equals is already there, I'm just going to put in the -1. Okay. All right. And again, if you have any questions along the way, just ask. So then part D, this is the notation for inverse function. So that is the inverse of f, the notation we use for that. And so looking at that, it does say to simplify our answer. So we got to figure out what it is. So the general process for inverses. Remember, for an inverse function, basically swap x and y, and then solve for what I call the new y, because the y is in a new place. Okay. So my original function was f of x, back up here, f of x. But remember, f of x is the same thing as y. Okay. So my original function is y equals common log of x plus 1 plus 3. So if I'm going to swap x and y, then those have to change positions. So that becomes x equals common log of y plus 1 plus 3. And now I'm going to solve for that new y. I need to get that y by itself. So we start doing opposite operations. So the first thing I see is that the y plus 1 is part of the input to the logarithm, but the plus 3 is on the outside. It's just added to it. So the opposite operation of that is just subtracted over to the other side. So I do that on each side, and that leaves me with x minus 3 on the left, and then the common logarithm of y plus 1. Now, this is where you want to be very careful. The common mistake I see with students at this point is they interpret the common logarithm of y plus 1 as logarithm times y plus 1. But that's not correct. You always have inside the parentheses something that goes into the logarithm. Remember, this is a base 10. We just don't write it. It's just known that it's a base 10. Similar to how when we write a square root sign, we don't put a little 2 as the index like we would with like a cube root. We just know that it's a 2. Same thing here. So that is not a multiplication of log, because you have to have a log of something times y plus 1. But what we do know is back from when I was doing problem 19, remember I talked about the definition of a logarithm? You can switch from log form to exponential form or vice versa. That's exactly what we're going to do. So we're going to use the definition of log to switch to exponential form. Okay, so that becomes, I have a base of 10, remember, that becomes 10 raised to what the logarithm used to be equal to, because what a log is equal to is always representing an exponent when you rewrite it in exponential form. So that x minus 3 that the log was equivalent to becomes my exponent. And I'm just going to go ahead and group that so it's clear that that whole expression is the exponent equal to the former input to the logarithm, which is the y plus 1. Okay, now that means y is just with a plus 1. So an opposite operation is subtract 1 from each side. So that leaves me with 10 raised to the exponent of x minus 3 minus 1 equals y. So I have now solved for y, and then I'm just going to replace that with the notation that we use for inverse function. So there is my inverse function. So I go back to my answer blank, and notice they already have the f inverse of x equals already written. So they've got this part written, which is the same thing as y. So I just need to write this part that is 10 raised to the x minus 3 minus 1. When you're entering that into MyLab, make sure you close off this exponent and then write the minus 1. So you might need to drop your cursor down and like move the cursor to the right to make sure you're not putting the minus 1 up where the exponent is. That's another thing I've seen students do, is just getting the notation right in MyLab with that, okay? And again, that's an exponential function. Exponential and logarithmic functions are inverses of each other. So it shouldn't surprise you that when you find the inverse function, it is written as an exponential function, okay? Now, in part E, we can find the domain and range of the inverse. So in general, remember, if you've got your function f going from domain to range, then the inverse function going backwards takes the same set that was the range and makes it the domain of the inverse, and takes the same set that was the domain of the function and makes it the range of the inverse. They swap, okay? Which is why algebraically, when we found the inverse in part D, we swapped x and y, because domain is x, range is y. So what this means is these set of values are the same, but represent different things to the function versus the inverse. Domain of function is the same as the range of the inverse. That also means this set of values is the same set of values serving two purposes. First, they are the range of the function, but they're also the domain of the inverse. So Since this is asking about the inverse, and it says to write it in interval notation for both of these, if I want the domain of the inverse function, then it is the same as the range of the function. That's like my blue circle over here. Well, we already found that. The range of the function was answer C. So it's that same answer, negative infinity, infinity, because these were the same, okay? Then the range of the inverse is the same thing as the domain of the function. Well, we also found that. That was the part A. Part A was the domain of the function, -1 to infinity. So it's that answer. And so these were the same. And so -1 to infinity. So it's making sure you understand that relationship. And then finally, we get to part F about graphing the inverse function. So you can do this a couple different ways. You can look at the inverse function and say, okay, what do I know about f inverse of x that is base 10 raised to the x minus 3 minus 1? And I'm going to ask the same question as before. What transformations have been applied to that? Well, if I compare that to a parent function, y equals just 10 to the x, I can see that a couple things have happened. Whoops, and to highlight, not scratch out. I can see that the -3, because it's affecting x, means horizontal. It's a subtraction, so it's a shift. And because it's horizontal, it goes against what my gut and my eyes tell me. I see the minus, I want to go to the left, but I actually do the opposite and I go to the right. So it's a horizontal shift right 3 units. Then I also see this -1 that the parent function didn't have. So then I say, okay, what is that doing? Well, that is at the end of the function, right? So the function is 10 raised to a power. And then outside of that, it's being subtracted by 1. So it's subtraction, and it's on the outside. So it's affecting y, so that's vertical. And because it's subtraction, it's a shift. And because it's y and vertical, what I see is what I get. So I see minus, I want to go down towards minus. And so this is a vertical shift down 1. So that's from the parent. So an exponential function in general has the basic shape like this. It has a horizontal asymptote at the x-axis or y equals 0 and has a y-intercept of 0, 1. So I could look for a graph that moves that point 0, 1 and the horizontal asymptote based on the horizontal shift right 3 and vertical shift down 1, because what that tells me is that this point 0, 1 would turn into horizontal shift right 3 means the 0 would become a 3, and shift down 1 means the 1 would become a 0. And the only thing that's going to affect the asymptote is moving down. That's going to become y equals -1. And so I can figure out that it can't be C, because it looks like that graph was moved up above the x-axis, and it can't be A, because that one was moved up. So then I'm down to B or D, but I can see that the horizontal shift should have been right, not left, and B is to the left of the y-axis, so it can't be that one, so it must be D. Now, the other way I can do this is that F and F inverse should be symmetrical across the line y equals x. So what I could have done is looked at the graph that I chose above for the function, and I could say, if I had the line y equals x, I can rotate over that and try and see what the symmetrical image would have been, and then find the graph down here that would have done that. That might be a little tricky on the computer, but maybe easier on paper. So it's best to work towards these transformations and use that to help you instead. And so that would be the last part of number 12. Okay. Any questions related to that number 12? So we have about 7-8 minutes left. If anybody else wants to see 13, I can certainly do 13 or 20. But again, the folks who asked for 20 and 13 said we can go ahead and skip those. So are there any other questions that any of you have that you want me to go over a specific problem? Otherwise, I can either start at problem 8 where the other review left off, or I can look and see like, hey, these are common ones that I know students have asked about in the past, and I'll just pick something and start with it. But I want to give you guys an opportunity to ask what you might have a question about since you're here live with this. So I'll wait a few seconds and see if anybody has anything they want to throw in the chat. And if not, like I said, I'll pick up where the other review left off, or look at ones that I think people might, have questions about based on past stuff. Can I do a commonly missed one? Yeah, I can do that. So I think a commonly missed one is actually number 13, now that I'm looking at that. And then number 14, I think, is also another commonly missed one. So I'm going to start with that. I think I have time to do both of those. And again, if somebody else has something else they want, I can certainly do that. But part of the reason why number 13 is a commonly missed one is they misinterpret where things go, or they type it into MyLab wrong. So those are kind of the two things that I see. So it says to express this as a single logarithm. Notice right now, there are 2 logarithms. Every time you see the word log or ln for natural log, that's one instance of a log. To be a single logarithm, you only want to see that word once, okay? And right now, we've got a base of 7. So we want a single logarithm and only have the base 7. Now, when you see a repeated logarithm like this, make sure the bases match. That's how you can apply these formulas from the formula sheet. So we've got a product rule, quotient rule, power rule, and change of base property. Notice the way this is written, they all have a base of b, meaning it's the same one. And so I'm going to apply the product rule. The reason I'm going to apply the product rule is because I see this plus sign. But before I apply the product rule, I'm going to apply the power rule, because I see an 8 and a 9 as a coefficient out in front of each of those logs. So I'm always going to do that power rule first before I apply either a product or a quotient rule. So what that means is that 8 and that 9 come back over to represent a power, not something multiplied in front as a coefficient, on their appropriate logs. So I would write this as log base 7 of u to the 8th plus log base 7 of v to the 9th. So the mistake I see students do here is they want to put this together as a product before they handle the 8 and the 9. And then what they do is they don't know what to do with the 8 and the 9. And so they think, oh, well, I'm going to use a product rule. So I'm going to bring these together. So let me just multiply the 8 and 9. And that actually doesn't work. Okay. So before you apply quotient or product rule, you want to handle anything that could come back to being an exponent with that power rule. Now, because I see this plus and I've got a log with the same base, 2 of them, I can apply the product rule. So this was power rule first. Now I can apply the product rule and say, okay, I'm going to bring these together as one logarithm with base 7 that is a product of the 2 former inputs. And so u to the 8th, b to the 9th. And that is what goes in this answer blank. And so then when you put this in MyLab, You want to be really careful that you get the subscript to be the base of the log underneath, drop down, and you have the little math palette button that comes up where you select things. So you select the one that looks like a log with a blank box down and then a box up. And then in the box that is up, make sure you put in these parentheses, and then make sure you put U raised to the 8th next to V raised to the 9th, and then you close that parenthesis. So again, you want to make sure your cursor is in the appropriate place. Is it in line? Is it an exponent? Or is it dropped down as a base? And that's, again, where I see common mistakes with that. Okay, so that's 13. So another commonly missed problem is 14. And this is kind of related to 13 in that I need to apply something where I get a single logarithm first. And so when I look at 14, I'm solving. I'm just not rewriting an expression, I'm solving. But what I see is I've got two logarithms on opposite sides of the equation. And I have this additional +1 on one of the sides. If I didn't have that +1, I could use the one-to-one property that I used earlier that said if m equals n, then log base, a or b of m equals log base a or b, whatever you want to use for the letter of n. So you can apply the log. Well, you can also remove the log, but only if they are independent with nothing else with them. When there's something else there, then your goal is to get the logarithms together on one side. So what I'm going to do is I'm going to take the logarithm from the right and subtract it to go with the logarithm on the left. And because I don't see a base written, again, it's assumed this is the common log, which is base 10. Now I have them together on one side. Then I start looking for my properties and I say, oh, I see a minus sign. That's indicative of the quotient property or quotient rule. So I can bring these logarithms together and consolidate this into one logarithm with base 10. So again, I don't have to write it, it's understood. That is the numerator x plus 7 divided by the denominator x minus 3, because you take the input of the first one, put it in the numerator, the input of the second one, put it in the denominator, and this all equals 1. And now from here, I can apply the definition of a log to switch forms. So I'm going to switch that from log form, which is base 10, into exponential form that has base 10. What the logarithm is equal to is the exponent, 1, equaling the former input, which is this fraction, 8x plus 7 over x minus 3. And now 10 to the first is just 10. And so I have this all equal to this fraction. And if I want to get rid of the fraction, I multiply on both sides by the denominator, which means I distribute on the left and I just get rid of the denominator on the right. So this is 10x minus 30. And now this is linear and much easier. So I just move things. I can subtract 8x, get 2x minus 30 equals 7, add 30 to each side. 2x is 37, and then I can divide by 2. Once you get it to a linear equation, that's much easier. And so I get 37 over 2. It says to type an exact answer, so I'm not going to use a decimal. Says, simplify your answer. And so this is my value that I get for that, okay? So I would get answer A, and the solution is 37 over 2. Okay, so that is it for tonight. I am going to have this recording posted tomorrow if anybody wants to go back and review anything. And if you want to attend the session that is tomorrow, you can do that. That is at 1:30. It's in the afternoon, so if you want to do that, you can. I'm going to go ahead and post in the link to the feedback in the chat. So if you want to give feedback on this session, you are welcome to do that. Good luck on your exam, and hang in there. You're almost done. And if you have any questions, don't forget to reach out to your actual instructor. So take care. Have a good evening.